Photoelectric effect, certain photosensitive materials have electrons that, when struck by high-energy photons, give the electrons enough energy to escape the material. Now, because this has light, which before this was classically thought of as a wave, hitting an electron and colliding with it, this is evidence that light can behave as a particle. This was first discovered by Albert Einstein, which is the discovery he won the Nobel Prize for. So in the photoelectric effect, a photon is incident on some photosensitive material, and that photon carries energy hf, where h is Planck's constant, and f is the frequency of the incident photon. When the photon hits the electron, it's going to eject it from the material it's in, and in order to do that, it has to expend energy. So this variable phi is the work function, which represents the amount of energy that the photon loses when it ejects the electron. So the equation for the photoelectric effect is basically just conservation of energy. It says that as a result of being freed by the photon, the electron will have some maximum kinetic energy K max, and that's equal to the original energy of the photon, hf, minus the energy lost in freeing the electron, which is phi, the work function. So the photon has energy hf, loses energy phi, all the leftover energy goes to the electron in the form of kinetic energy when the electron moves off from the material. Frequency and wavelength of light are inversely proportional. So light that has a low wavelength has a higher frequency and will eject electrons that have a greater kinetic energy than high wavelength light, which has low frequency. On the other hand, when light is more intense, there's no effect on the kinetic energy. Higher intensity light or brighter light just means there's more photons, so there'll be more electrons ejected, but with the same kinetic energy as if the light were lower in intensity. If an incident photon doesn't have enough energy, it's not going to be able to eject an electron from a material. So each material has a threshold frequency, which is the minimum frequency needed by photons to eject electrons from the material. At the threshold frequency, the kinetic energy of the ejected electron is going to have zero kinetic energy, and that means that all the photon's initial energy goes to overcoming the work function with no kinetic energy left over, which means that in this case, K max is 0. So if hf minus phi is 0, then the formula for threshold frequency then becomes Planck's constant over the work function of the material. Another quantity that's commonly asked for is stopping potential, which refers to the amount of voltage needed to stop the electron after it's ejected from the material. For stopping voltage, the stopping voltage is going to do work, which will take all of the ejected electron's kinetic energy away. So the work done by the stopping voltage on the charge is the stopping voltage times the charge of the electron, which is the elementary charge. And since the kinetic energy is decreasing to 0, delta K, the change in kinetic energy, is just equal to K max. Often for the photoelectric effect, the maximum kinetic energy of ejected electrons is plotted versus the frequency of incoming photons. And the equation for photoelectric effect is basically slope-intercept form. So here, K max is equal to the y variable, frequency is the x variable, which means that the slope of any photoelectric effect graph will be Planck's constant, and any graph like this for any material will all have the same slope of Planck's constant. The y-intercept down here is equal to negative of the work function. Now at the x-intercept right here, this is where the kinetic energy of ejected electrons would be 0, which means that the x-intercept is equal to the threshold frequency. And then anything below the threshold frequency on this part of the graph would have no electrons. Here's a pretty typical photoelectric effect question. It gives the work function of a certain metal as well as the wavelength of photons hitting this metal. Part A is asking for the maximum kinetic energy of ejected electrons. So the formula is that kinetic energy is HF minus the work function. Now in this case, I'm going to have to convert the work function in order to keep all the units in joules. And then I'm giving the wavelength, but the formula uses frequency. So I'm going to use the fact that speed of light equals frequency of light times wavelength of light, and rewrite this as Kmax equals h speed of light over wavelength minus work function. And I get a maximum kinetic energy of 3.2 times 10 to the negative 19 joules. Now, if I wanted to solve for stopping voltage, I could set the stopping voltage times the charge of an electron equal to Kmax. And then I would get a stopping voltage of 2 volts. Part B asks for the minimum frequency of light to eject photoelectrons. This is asking for the threshold frequency. So at the threshold frequency, the kinetic energy is 0. The threshold frequency is then Planck's constant over the work function. And I get a threshold frequency of 1.0 times 10 to the 15th hertz. In the next example, there's a beam of light directed at metal, ejecting electrons, and it's asking which of the following will increase the kinetic energy of the electrons. Well, A and B are referring to intensity of the light, which doesn't affect kinetic energy, so I'm going to cross those out. And then for more energetic electrons, I want more energetic photons. So the energy of a photon will be higher when the frequency is higher. And then in order to have a higher frequency, I want to have a lower wavelength. The last example gives a graph of the photoelectric effect with kinetic energy versus frequency. And it's saying, how would the graph change if the work function were to increase? So the work function is going to affect the x and y intercept. Choices C and D refer to slope. The slope for any photoelectric graph is Planck's constant, so that will never change. And then down here, the y-intercept would be the work function. If I were to increase the work function, the graph would shift down, which means that in this case, the x-intercept of the graph would increase.